welcome Shailee Goswami from Saint-Gobain. She comes from Saint-Gobain R&D. Oh, and well, she's not located too far from here. She's in the same IIT Madras Research Park. Saint-Gobain has set up a research division. My pleasure to invite her. I want to listen and learn as much as you guys want to about what large firms, some of the largest firms in the world, what they are doing when it comes to low carbon, when it comes to sustainable, and when it comes to decarbonizing the products. Shailee, I welcome you.
Hi everyone, a very good afternoon. My name is Shailee Goswami and I'm currently leading the building science team with Saint-Gobain Research India. As a part of our portfolio, of course, I come from the background of materials manufacturing organization. I'm sure you must be knowing Saint-Gobain about manufacturing glazings. But it's way beyond that. Of course, we are manufacturing various different kind of high-performing materials that go in the built environment, which is the buildings. So in today's presentation, I would briefly take you through the kind of work that we are doing for designing low-carbon buildings. Basically, what can be the So primarily the focus would be about how can we design low carbon buildings, and most importantly, how can we calculate or quantify the carbon emissions which are associated with constructing a building. So I just wanted to start with setting the context over here. I think you all might have seen these numbers somewhere, right? That buildings are contributing close to 40%, more than 40% of national greenhouse gas emissions. So that's one of the metric that we all would be coming across. But at the same time, what is an opportunity for us is the fact that 70% of India is yet to be built. So this provides us with a lot of opportunity to build better, to build sustainable, and even construction materials which are emitting low carbon. So in terms of the problem statement, basically the kind of problem statement that we have right now, there is too much of material construction demand which is needed because we have to construct so many buildings in the coming years. And in order to construct these buildings, of course, there's going to be a lot more requirement of building materials. And that's exactly where it's important for us to create sustainable alternatives and even low carbon alternatives that can go inside a building. And of course, you all must be aware of the net zero targets which are being set that we have to cater to by 2070. So this will certainly help, and it poses as one of the key requirements right now. So what is the current need? Of course, we need India-specific LCA frameworks, which is the life cycle carbon emissions. And of course, we have to understand and think about adopting it at a larger scale. So with this, basically, we tried to come up with a model which fits the Indian context, right? Because there are many calculations and standards available in the market right now, but they are all catering to the European standards. And we cannot simply copy-paste the European standards to India because, of course, our needs and requirements are quite different. So with that in mind, we of course wanted to start somewhere, and we took up ISO as our base standard with which we can start working and keep our LCA frameworks for. So this basically has three main stages. One is the A1 to A3, which is associated with materials. The next stage is the B stages, which is B1 to 7, which is about use case. And then comes the C stage, which is end of life. And then the last one, which is beyond life cycle, which is the stage D. So for our study, basically, we took an example of a building, so for which we kind of did the calculations which are very regional, very India-specific. And what we did was, this is the kind of framework that we took up and adopted for our study. So here we took these stages for our calculation purposes. So when you say A1 to A3, which is at product stage, we have considered what happens if you use different kind of materials throughout this production stage of the building. Then we have A4 to A5, which is the construction stage associated with the transportation, construction, assembly. B1 to B5 is related to maintenance, repairs, replacements, and refurbishments. But of course, we have taken and we have kept our focus mainly on glazings and walls. But at the same time, it requires much more, but our study, we have kept our scope limited to this. Then the other stages are associated with mechanical systems. Then B7 is for water, C1 to C4 is for demolition, which is the entire cycle of the material, and the D1 is beyond life, which we are not considering for our study. So this is the basic framework that we have taken up for our analysis. Now let's get into what we have done actually. So this is an office space that we took as an example, which was situated in New Delhi. So it's an actual office that we have taken for our study because it's easier for us to get the bill of quantities, the quantity of material which is going inside it. We have used our simulation models to create an exact replica of the structure. And the model that we have primarily used is Energy Plus, one-click LCA. Rhino and Grasshopper is primarily used to create the geometry of the building. And this office space was basically operated during the conventional hours of 9 to 6, and it was constructed in 2014. So of course, one of the key problems that we also had was about gathering the data. It gets very difficult to get the quantity of cement, steel, concrete, which is going inside a building which is already constructed. So then in our simulation models, we have to set the assembly parameters. So at first, we have to define the external wall, which is of brick. Then we have internal wall systems, which is gypsum partitions and plywoods. Then we have other things like structural, flooring, windows. So these are the exact parameters that you need in order to define your model accurately. Then when we talk about the model inputs, or I would say more about the mechanical systems inside a building. So we have taken the conditioned area to be 223. So the whole office is not conditioned. Of course, some of it will be naturally ventilated. Then we have taken the values for lighting power density, which is the watt per square meter. It's basically how much of light fixtures are you using in your building. Then the second one is the equipment. How many equipment are used inside it? And lastly, and most importantly, is the HVAC system. Now what we have analyzed is we did substitution with conventional walls. So in India, our predominant wall systems are brick. Then of course it is aluminum is catching up quite fast. You see a lot of Maivan work ongoing. People are constructing walls with concrete. There are some high-performing alternatives available. You have fly ash brick, there are autoclaved aerated concrete, which is AAC bricks, and then there are also gypsum walls, which are certainly low in terms of carbon, one is of course the embodied carbon, which is the upfront carbon, and second is the operational carbon, which is throughout the life cycle. How much of impact will it have on your air conditioning? Because if you're using a better wall, you will certainly save in your air conditioning bills. That is more about the operational expenses. At the same time, you will also save quite a lot in terms of your capital expenses, because if you're using better building materials, you can certainly save in even reducing the tonnage of your HVAC system. So with this concept in mind, we wanted to understand what would be the impact of these alternatives over the life cycle carbon emissions of a building, which is for 60 years of the life of a given structure. We also did some alterations in terms of glazings. Glass, of course, lot of solar radiation comes in with it. It gives a lot of good light and good view to the outside, but at the same time it brings in heat, which is a big problem, right? And it has a direct impact on the HVAC consumption. So we tried out 6 different cases. The first case was a single glazed unit, which is predominantly used in residences. And then we also have an alternative of a double glazed unit where there is an air cavity between 2 glasses. Now that configuration is very common in commercial spaces or high-end buildings like even educational or hospital buildings. So we did this analysis, And so these are the results for the overall carbon emissions throughout the different life stages. So as you can see over here, the embodied carbon emissions from A1 to B5 were approximately 32%. And if I have to further bifurcate it, A1 to A3 was 22%. But the majority of it was B6, which is the operation. So over the lifetime of the building, which is 60 years, the majority of your carbon emissions would happen at that stage, which is B6. You can see it's around 68%. Now let's look at the bifurcation, if we want to see, okay, which component is contributing the most in this emission. So on the right, what you see is a system-wise breakup. So here, the majority of the carbon emissions are, for embodied carbon, are coming from roof. The reason is because roof contains the maximum cement, concrete, and steel, which are basically the hotspots of carbon emissions, especially the embodied carbon. And this is exactly why we need very solid interventions in this material segment, which is concrete, cement, and steel. This is followed by windows, of course, because it's glass, and the frame. We use metal frames, right? It's steel or aluminum frame in the windows. Then it is, of course, external walls and finishing and so on. So as material manufacturers, we just want to analyze and see how can we substitute this material so that we can bring down the emissions. So what we did was we tried out various different options. On the left, what you see is the embodied carbon. On the right, what you see is the operational carbon, which is throughout the life cycle of the building. So for embodied, basically, you can see this comparison. Brick has the highest emission, followed by concrete, fly ash, gypsum walls, and the last one is AAC. So the autoclaved aerated concrete block is able to significantly reduce your embodied carbon emissions. So that's upfront, right? But what about the life? Okay, that's like one time you're installing or you're constructing a building with these materials. But what happens over 60-year lifespan of any structure? So if you look at it, the concrete is consuming the highest energy out of all the options, followed by the brick and the fly ash brick. So essentially, what is important for us coming from the construction background is to have an holistic view of materials and then make the right set of decisions. The same thing, what about glazings? So when we think of the single glazed unit versus the double glazed units, you can see single glazing, of course, will have lower energy because it's single glass, right? And the moment you have double glazings, it will almost double your embodied carbon. But the same thing, if you look at it more from the operational standpoint, you can see the single glazing will have more energy consumption because it is bringing in more heat inside the building. So with this in mind, I in fact tried to also conduct a combined assessment of embodied carbon on the x-axis and the operational carbon on the y-axis. So when we look at the embodied carbon, the first plot is for glazing systems. So here you can see the embodied carbon is not changing that much. The data points are basically quite in line. But the other thing that you can see it change quite a lot is the operational emissions. So that's why it shows that the selection of glass can have a big impact on the operational emissions of the buildings. Now the same thing if you look at it for walls. So here in walls, you can see a fair distribution. In fact, if you are going for a wall like AC, it can help you not only reduce the embodied carbon, but also the operational carbon. And same thing goes for lightweight gypsum walls as well. So this is the results, and what you see over here is I've also tried to add the benchmarks in the country, right? So we at present the threshold that we have for the emissions as per the IGBC, which is the Indian Green Building Council. So there is a threshold that they mention is around 700 kg CO2 emissions. Which by the way is very, very stringent. I mean, if I compare it against the global standards, it's very stringent. Even other countries haven't set such hard thresholds. But you can see that certainly it's still not under the given threshold, and it basically emphasizes on the fact that how much we have to do as a country, as a construction industry to make sure that these emissions are quite in line and checked. So I would come to the last part of my presentation, which is what is the key insight from this whole analysis. So one is definitely the operational carbon dominates. And of course, embodied carbon is very, very important and it is the need of the hour. But at the same time, it's very important for us to look at it very holistically, even from operations point of view. Then system level hotspots are very important. We need to further bifurcate and dissect the data, that who is the key culprit of it and what can we do to kind of substitute it and make it better. Of course, material substitutions can help a lot. We showed that it can help you achieve up to 26% of reduction, but at the same time, I think we have a long way to go. And then lastly, of course, policy and data gaps, something that our country is trying to catch up to. We are coming up with stringent policies, but its application is something which is still needs to be kind of checked. So what is the way forward for us? It's of course the immediate one is to make it more mainstream. We have to integrate it into our policies and codes. Long term is of course we have to strengthen the data. One of the key pain points is the accuracy of the data that we have. Later on in future, of course, we have to kind of focus on high impact systems, and we need to bring in more innovation in the building materials industry. So that's it. Thank you so much. I'll be happy to take up any questions.
You can come over here. You can sit for a couple of minutes, maybe a few questions, mainly from me as we're running out of time, but I'm sure those guys can catch you before you run to catch your flight. So I'm not going to go deep into this because these are all fairly detailed, and I'm sure each of these graphs you showed and the breakups or discussions can go on. Just one question, since you come from the R&D side. So if I were to ask you, be it operational, be it embodied, breakups, all those, yes, I mean, I learned a bit, agreed. What science do you think is going to make a difference to the materials that you build? Is it nanotech, is it AI, is it chemical? Because as you pointed out, what you guys do, Saint-Gobain and similar large firms, can make a difference both to embodied carbon and to the operational carbon emissions. But what one or two scientific concepts or principles you think it will drive? Is it metallurgy? Is it nanotech? Is it AI? I mean, is there something that you can share with us based on what you guys are doing?
So I think each one of these segments that you spoke about will have a key role to play. So let me start with AI first. So in terms of AI, we can certainly make use of it in terms of correcting the data that we have right now. Because if I say one of the major problems that we have at the moment is the accuracy of data for now. So for example, if I take cement, so the database for India for cement industry can vary a lot depending on the location. So it gets very difficult for us to identify how accurately it is being calculated. So we certainly need a very big scale of data scraping of all the databases available across the country. We need a clear-cut benchmark of how accurate are they and how far what we can do to basically improvise on it. So we can certainly do a lot of data processing, and AI can certainly help in that in terms of getting us the right set of data for these calculated numbers. Second is you also mentioned about nanotechnology and for that matter even the chemical way. So there's certainly a lot more that we can do in terms of material innovation. So for example, again I would take example of cement because that's one of the key hotspot. So in order to reduce the emissions in cement, we can certainly maybe add some kind of admixtures that can further help in reducing the use of cement altogether. So we can completely change its composition itself, or we can maybe do some interventions in terms of the concrete composition, for example.
That might be more on the material tech, nanotech, etc.
Absolutely, absolutely. There are clear-cut innovations which are needed in terms of high-performing materials.
Interesting. We can go on, but I think your flight isn't going to wait for you. Thank you very much, Shailee. Thank you very much
so
for being here. Yeah, well, only one question, because you don't want to be the person who made a miss a flight, right? Yeah.
So I think there would be like a bit more explanation needed for this. So I'll be very happy if you can please catch up on my email ID. I think they have just taken it off from the screen, but we'll certainly connect on that. Thanks a lot. Thank you.
Thank you, Shailee.
I
Thank you for being
request
here.
Mr. Sumit Bhatia from ARS Steel to come and present our memento to our speaker.